So our next speaker is Daniel Ritchie from Brown University, giving an invited talk on learning neurosymbolic 3D models.
All right, thanks, Vikas. Thanks for having me. Let me go ahead and get the screen shared. All right, there we go. All right, so the topic of my talk today is really all about generative models of 3D objects. That's what I'm interested in telling you about today. And why is this a thing we should care about? Well, so I'm a computer graphics guy originally, and in graphics, there's a bunch of applications of capturing generative models of these things. So you can use them for design exploration. So here's a 3D generative model that allows us to sort of continuously explore the space of possible car shapes. And they can also be used to do content creation at a very large scale. So we can use something like Esri's City Engine to rapidly generate, life-size virtual cities. And in artificial intelligence, actually, there's a bunch of applications for them as well. Of course, we can use them as strong priors for vision systems. So if I have some sort of 3D scanner that's trying to understand the structure of objects in the world around me, it might miss various regions for different reasons. Insufficient scanning, maybe the surfaces are specular instead of diffuse, and so the scanner doesn't pick them up. But even with these sort of incomplete scans, we can end up with, we have a strong generative model of these kinds of 3D shapes. We can infer what the missing structure must have been. And they're also being used to create environments, synthetic environments for training autonomous agents in simulation before deploying into the real world. So one high-profile example of this is Facebook AI's Habitat environment, which is a sort of a first-person simulator for embodied navigation agents. So that's kind of why to care about this problem. So how do you actually build generative models of 3D objects? Well, classically, this is a discipline that started in computer graphics. We would use procedural models. So basically programs that output geometry. So here's an example of a recent-ish paper on procedural modeling of architecture. And I actually did my PhD on procedural models as probabilistic programs, doing things like trying to use inference to find executions through these shape-generating programs which would match certain 2D silhouettes, or would avoid certain regions of space, or would be physically stable, even if the structures seemed kind of initially visually precarious. And so there's lots of advantages to this kind of representation, because you have some programmer who's written it and presumably knows what they're doing. You're going to get high quality geometry output by construction, and these things can't generate garbage outputs. And because they're human readable text, the representation is interpretable and it's editable. I can look at different parameters in the program and I can make changes to them and I can see what effects those changes have. But there's a lot of disadvantages as well. So these are difficult to author. You do need to be both an expert in geometry and also to know something about how to program. And there's a limited output variety. It's difficult to write one program that captures all possible shapes, even all possible shapes within a particular object class. It's hard to think about how I could write a single program that could generate, for example, all possible automobile shapes. So lately, because of these limitations, deep neural networks have kind of been the king in this space. We've seen over the past few years, we've seen work on generative adversarial networks, which create sort of volumetric grid representations of shapes. Improvements of this idea, which use adaptive resolution grids to generate even higher level detail. Point cloud generating networks, networks that generate 3D objects by a set of surface patches or by deforming a continuous 2D mesh to a particular shape. And even more recently, there's been some really cool work on neural networks that represent infinite resolution implicit surfaces, essentially a distance function that tells you how far away you are from the surface. And there's a lot of compelling reasons to use these. it's very easy to capture variety. Essentially, any class of shape, in theory, can be represented by one of these networks. And they're easy to author in the sense that once someone has provided you the network architecture, the way you author a new generative model of a particular type of object is you just add data. You just give it examples, and it takes care of the rest. But of course, there's no free lunch, and there's plenty of disadvantages as well. The main obvious one is that there can be very inconsistent output quality. These are deep neural net models that are trained with stochastic gradient descent, and they often have holes in their parameter space, which result in holes in their output space. So we can have examples of disconnected parts, floating parts, excessively blobby geometry. There's lots of problems here. And of course, the other thing is that the representations that these networks learn are totally inscrutable. We don't really know what the neurons represent, and the only way we can really interrogate them is by poking around in their latent space. And so if we look at these two classes of generative model, the goal, I would argue, is to figure out how can we get all of these benefits of both classes of model without any of these drawbacks. And so what I've been looking at in my group recently is sort of a best of both worlds approach that I like to call it sort of a neurosymbolic 3D generative model. So if we look at this problem that we identified, that procedural models are hard to author, one way you can propose solving this is to say, well, let me just train a neural network to write programs for me. So the shapes will still be represented as programs, but a neural network will generate them for me. And if we have this problem that a single procedural model can have limited output variety, in this paradigm, that's okay, because the latent space of this neural network is going to capture modes of variability that one symbolic program does not. So we're going to have a bunch of different symbolic programs which are all correlated through this neural latent space. And this idea was at the center of a paper that my group recently wrote that we'll be presenting at the SIGGRAPH Asia conference in a couple of months about the system that we called shape assembly. And the name for this, it sort of has two meanings. So it's an assembly language for part-based shapes, in the sense that it is both kind of low-level instructions, like a computer assembly language, but also that it operates by assembling parts. That's the fundamental metaphor that it uses to construct these shapes. So we can look at what an anatomy of one of these programs looks like, and essentially what we have it's a hierarchical program. So at the root we have a set of boxes that are connected together. So here I use operators like cuboid to declare these boxes, and I have operators like attach, which specify how these cubes are attached together, and these little red dots are showing where the attachment points actually occur. We have some higher level operators like squeeze, which specify that a box is attached on two sides. That's what's going on with this one. It's sort of attached on the top to this pink box, and on the bottom to sort of the overall bounding box of the shape, which is not visualized here. But what's cool about this is that some of these boxes can be stand-ins for subroutines. So in this case, this dark gray box is a stand-in for a subroutine called base. And we can actually look at how that's defined, and that actually expands into another subprogram which defines these four legs. And if you look at how those are defined, we actually use we sort of define these two front legs and two back legs. That's what these lines are doing. But we have these reflectional symmetry operators which duplicate them, so that we end up with four legs instead of just two. And a similar thing is happening. We sort of recursively descend into this back cuboid to create this shape here, where we have a translational symmetry group which creates these three slots here. So it's kind of the idea here is not to represent geometry in its highest level of fidelity. We're looking just sort of at structure. So what parts are there and how they're connected. But the idea is to use this language that has sort of in the structure, the way that it's designed has sort of guarantees a certain physical plausibility in how these shapes are assembled. And then what we do is we train a neural network, and this architecture, if you squint at it, and you don't kind of pay too much attention to these details, is a variational autoencoder. So it's a probabilistic generative model. And this variational autoencoder is trained to write these programs. So we're trying to sort of take all these programs and project them into a unit normal latent space. So our prior is a unit normal distribution. We sample from this prior, and we can decode different programs. And so, the way that the VAE is trained, you have an encoder and a decoder. The encoder is just it's a recursive neural network that kind of recursively aggregates and summarizes these hierarchical programs, this sort of hierarchy of text sequences. And then the decoder just undoes that process. It's another sort of top-down recursive neural network, which uses, again, just a sequential language model to generate each line of each level of the output program. And if you take a look at what's inside these purple boxes that say line decoder, this is probably what you'd expect. It's just a big switch statement that looks at, we first try to decode what type of command we want to be outputting, whether it's a new piece of geometry or it's an attachment or a squeeze or symmetry groups. And then depending upon what command we output, we have different submodules that learn to predict the parameters of the arguments of these different commands. That's basically what's going on there. So what can you do with this when you've got this language and you've got a model that generates programs in the language for you? Well, the first thing we were interested in is doing novel shape generation. We wanted to be able to use this to create new shape structures that had never been seen before. And so here's an example of some samples. So if we just sample from the unit normal prior and then run it through the decoder, we get these output shapes. And we can look at how they compare to their geometric nearest neighbor in our training set. So this is just based on a 3D surface-to-surface distance metric. And we can also look at how they compare to their nearest neighbor in program space. So basically an edit distance between the programs. And in both cases, there's similarities, but these are not identical to either of these forms of nearest neighbor. So we're getting some novelty that's not just memorizing the training set. We can also do a really interesting form of structure-aware interpolation between shapes. So if I start with an object, in this case a chair that looks like this, and I have an endpoint, which is this target shape, I can then just draw a line segment between the latent codes for these two shapes in my latent space, and then I can sample along that line segment and decode the codes that I get along the way. And I get a really interesting behavior where the shape, geometrically morphs from the source to the target, but in the process of doing so, it also introduces these discrete transitions between structures, because we start with a chair that has a flat back, and we end with one that has this sort of 5-slat back. And we can see that, I'm only subsampling the trajectory here. But at some point, we introduce these 2 slats, and then 4, and then 5, and then we kind of make them longer in order to get closer to the target shape. So this is nice because these non-structure aware shape generative models that I was showing earlier can have this problem where, in order to interpolate between a flat back and a multi-slatted back, they would probably start to introduce some implausible holes in this geometry. Whereas this model, by construction, has to produce these kind of plausible part assemblies. I also claim that the nice thing about procedural representations is that they're interpretable and editable. So we can take some random samples from our generative model. I'm not visualizing the programs here. I think it take up a little bit too much space, but if you take my word for it, there are programs that underlie each of these shapes. We can edit some of their continuous parameters to produce variations. So here we've changed the number of repetitions of the symmetry group from 3 to 5, and we've adjusted other sort of box size parameters. And similar edits were performed on these other shapes. So it's relatively easy to make these changes, as opposed to if your output was, say, an unstructured mesh or a volumetric grid, it'd be very, very difficult to make these kinds of edits. And as sort of like a bonus application, I mentioned that you can use these generative models as priors for vision systems. So we kind of tested out that idea here as well. So here we have as input an unstructured, unlabeled point cloud of an object in the same category. And we can essentially train another encoder that maps these point clouds into the latent space of our generative model. So if we project these to our latent space and then run our decoder, we get outputs like this, which are close-ish to the right shape. They have some problems, and what's actually quite nice about our system is that the interpreter, the sort of the runtime that executes these shape assembly programs, is actually completely differentiable with respect to the parameters of the program. So once we get one of these programs, we can then just optimize its parameters so that the output geometry, the output shapes we're seeing here, do the best job they can at fitting these point clouds in a sort of point to surface matching distance kind of way. And so if we do that form of optimization, we get results that look like this, which I'd argue are pretty close to about the best representation of these point clouds you can do within the space of shapes that's capturable by our language. And of course, the outputs that you get here are still editable. They're still physically plausible. These things are stable under gravity and things like that. Yeah, so that's really all I'll say about the details of this thing we built recently. I know I don't have too much time, so I just wanted to spend a little bit of time talking about what I think is next in this area. And I think that there's actually quite a big open design space of sort of neurosymbolic forms of modeling for 3D content. So if we this bubble represents the possible design space, really what I've talked about today has just been mining out this one little pocket of it, which is these neurosymbolic models of shape structures, right? What parts are there and how are they connected? And there's still a bunch of interesting stuff that we're still hammering on here, but it's worth taking a step back and thinking about, what else is there? What other attributes of 3D shapes are there that are worth modeling in this way? And I'd argue that, if we drill down into those, what's inside those individual boxes that our shape assembly programs are generating, we could talk about neurosymbolic models of fine scale part geometry. So some of these chairs, for example, actually have curved surfaces. Sometimes these things can be represented via CAD programs, things that declare parametric primitives like cylinders and spheres, and then operate on them via their unions and intersections. But also, sometimes that's not quite enough. There are even finer scale details that are difficult to capture with just these CAD programs. And so having a combination of, say, a CAD program with a neural network that kind of adds the fine scale details on top, I think could be a really valuable way to go here. And then you can look beyond just geometry and start talking about surface appearance, about the sort of surface texture of an object. And there are definitely really powerful procedural representations of texture for defining regular patterns, things that look like noise, wood textures, things like that can all be represented procedurally. But there's often a sort of a fidelity gap between the output of the procedural system and what you really see in the real world. And I think that, again, deep generative models could sort of close that gap for us. We could have a procedural representation of surface appearance that gets us most of the way there with a neural network that kind of captures that remaining delta to get real world fidelity. And I think the sort of the holy grail of this space would be some sort of joint generative model which couples all of these, so that we can have this really rich and structured, interpretable generative models of high fidelity 3D objects. And I really believe in this approach, and I think that as the Mandalorian would say, I think that this is the way. So I think my time is just about up, but I'm happy to take questions if people have them.
Thank you for a wonderful talk. We have one question. If you can give a brief answer to it, would be great, which is how does the decoder ensure the generated program actually runs to completion?
How does, yeah, that's an interesting question. So, in theory, if it's just a generative, if the generative model is just, learning to output things line by line, it could, in principle, generate something that, loops infinitely. In practice, if the training data never contained a structure like that, in practice, we don't see it happen. So, as long as your data doesn't contain those kinds of patterns, you're not going to get it in your outputs.
Maybe analogous to PCFG learning approaches.
Yeah. So it's a little similar to that, exactly.
Okay. All right. Thank you very much.
Thanks for having me. It's been great.